Yes, hi. Hi, everyone. Good morning. All right. So, what was the last part that we have discussed? What did we study in the last session, guys? Yes. What was the last part that we have done? Model evaluation. In the last session, that is 22nd, yeah, we have done knife bias, no? And it is completed, right? Is it completed or not? Knife bias? Yes, guys. Is it completed or not? Knife bias? Okay. All right. So let me open this. Very first thing is I'll just open this. Yeah. And let me check. Yeah, it's completed, right? We are getting 98.5% accuracy. All right. Okay. All right. So what we'll do is we'll quickly start with another machine learning model in today's session, that is SVM, and we'll just understand its intuition, how does it works, and we will work on one very important project out there, right? Very important one, a very useful one, rather. So what I'll do is, for you guys, I will quickly create the folder. Let's rename this as day 24, 20th December 2024, and let's call it as SVM because we are going to start with another machine learning model in today's session, right? Now I'll just upload the presentation that we are going to uh, use so that you can also refer. So the presentation that we have is SEM, this one, this one. Yeah. So I'll just open this and let us start working on this. Okay. We will also require, we'll also need the the Google Sheet for machine learning, this one. Perfect. So let us start with this. It is very useful machine learning model. So we call it as 23rd December SVM. All right. Yes. Let's start with this now. So you already have studied some well-known classification models. What are the different classification models you have studied till now? Yes, guys. What are the different classification models that you have studied till now? Yes, we have studied logistic regression. That was classification model, right? We have seen naive bias. So, though these models are widely used in the industries, such as in banking, in e-commerce sector, etc., and applications such as default prediction or text classifications, they find limited use in more complex classification problems such as image classification, right? SVMs, as you will see, are capable of dealing with quite complex problems where models such as logistic regression typically fail, right? SVMs have been extensively used for solving complex classification problems such as image recognition, such as voice detection, etc. And SVM are mostly used for classification tasks, but they can also be used for regression, right? So it is used to solve seemingly complex problems, but it's not the case that it is only used for classification. They also can be used for regression, but mostly we go for classification task, right? Mostly we'll be dealing with the classification problems. So in this model, you'll apply SVM to image classification, right? Image classification will be applying our SVM to image classification. So in this session, you'll understand hyperplane in two dimension, that is 2D, hyperplane in 3D and n dimension, and we are going to see maximum or maximal margin classifier concept, right? So that is our agenda. Now let us start with this. So SVM is a class of extremely popular classification models. Besides their ability to solve complex machine learning problems, they have numerous advantage over other classification problems, such as ability to deal with computationally heavy data sets, classifying non-linear separable data, and we'll discuss some of these problems in detail in the upcoming session, right? So it is important to remember that SVM belongs to the class of linear machine learning models, right? Which introduces linearity, which uses linearity. So SVM belongs to class of linear machine learning models, right? The logistic regression is one of the linear regression model. It is also linear model. Uh, in linear model, we use a linear function, that is y is equals to mx plus c, right? And to model the relationship between your input x and y, right? For example, in logic regression, the log odds of an outcome, uh, say defaulting on a on a credit card, is linearly related to the attributes of x1, x2, xn. So in logistic regression, what we have discussed, we used to find the log odd ratio. So log of odds of default, that is beta 0 plus beta 1 x1 plus beta 2 x2 plus so on plus beta n xn, right? So similarly, SVMs are also linear models. In the upcoming session, you'll learn to use how SVM use for SVM for classification problems, right? So this is theoretical part. You can read about this. I just have explained this. What is SVM is in very simple words. Suppose you have two classes. One is this white sheep, right? White sheep, and another is black sheep, and you have to classify them. So very best way is to draw a boundary. Very best way is to draw a boundary which will classify these two classes, right? Right? Classes one, classes two. Yes or no? The very best way is to draw a boundary which will classify these two classes. So this boundary will help me out to classify this into two group, right? And that is how your SVM solves the problem. So you draw your data, you plot your data into X and Y axis. This is one of the meme that we have. You can read this afterwards. I already have shared this on your drive. Then, yes, then let us understand the terminologies associated with SVM. Terminologies associated with SVM. So what we'll do is we will be uh, understanding what is margin. First is margin, second is hyperplane, third is support vectors. So very first thing, the hyperplane. It is a plane or it is a decision boundary. It is a plane or it is a decision boundary which we draw to separate two classes into class 1 or class 2 like this, right? It is a plane or decision boundary which we draw to separate two classes, class 1 and class 2, right? Then second is margin. So the nearest data points from the decision boundary, nearest data point of this class, nearest data point of this class is known as the support vector. So what is the support vectors? It's a data point which is nearest to the margin, the nearest to the hyperplane, right? It is a data point which is very close, first data point close to the hyperplane. And third is margin, and margin is quite common. On by the name itself, you'll understand what is margin. It is nothing but the distance between support vector and hyperplane. That is your margin. So we have three concepts: margin, that is distance; hyperplane, that is decision boundary; and support vector, that is the closest data point with respect to your hyperplane, right? So that is what we have here, right? Now, SVM comes under supervised machine learning. SVM comes under supervised machine learning. SVM can perform both classification and regression tasks. It can perform both classification and regression tasks. The goal here is to create best decision boundary that can segregate n-dimensional space into classes so that we can easily put new data into correct category or hyperplane. It is also known as out-of-the-box classifier. For better understanding, we'll learn maximum margin classifier, support vector classifier, and support vector machine. So at this point itself, only remember these three terms: margin, hyperplane, and support vectors. We have margin, we have hyperplane, and we have support vector. Now let's see a transition between different dimensions. This is 0 dimension, this is 1 dimension. From 1 to 2 dimension, if you go, we have a plane like this. From 2 to 3 you go, you have a cube like this, 3-dimensional space. And from 3 to 4D, it looks like this. So it is not properly, uh, our human eye is not capable to see 4 dimension, right? So that's the reason we restrict up to only 3 dimension, right? Now let us take one example to understand the SVM in better sense. We have x1, we have x2, and we have category. So we have x1, we have x2, and we have category, right? So what are these? These are the marks in the score, marks scored by students in x1, marks scored by student in x2, and whether the student is pass or fail. So let's say student 1 is 60, he has scored 16 x1, 82 in x2, he has passed, right? It is passed. Then this is 20, this is 42. So this student is failed, right? Then this is we have I mean it suggests that we have n number of students over here. Then we have student who has scored 91, 72. So obviously it is pass, right? Now what we want to do is we want to visualize this data in such a way that we should be able to classify the data points into two groups. So we have just plotted data on x and y axis. We have just plotted data on x and y axis, right? So x1 is the marks scored by student x1 and x2 is marks scored by student next. And what we are interested to do is we are interested to draw a decision boundary. Interested to do to draw a decision boundary which will classify these two data points here and here, which will classify these two data points, right? So that you'll understand this student has scored. I mean, you are clearly able to separate two classes by using the decision boundary, right? So that is what our aim is. So there are many possible ways to separate the two categories of classes, right? Yes or no? There are many possibilities to separate the two classes, two category classes. But which is best among all? Which is best among all? How can we find this? We can find this by, let's say we have multiple ways to plot a line, right? This is 1, this is 2, this is 3. So I'll just zoom it a little bit. Just a minute. Yes. Now, if I take this, if I take this line, this decision boundary, uh, I am clearly able to separate the two classes. The distance between my support vector and hyperplane is very less, right? On the other hand, if I just take this is good, right? And if I take this is also fine, right? So which one we should take? In order to understand that, we should remember this rule that we cannot predict the best possible hyperplane. So the solution for the problem is the hyperplane, right? It can be picturized by the below figure in generalized way. So the idea here is to select a plane, select a hyperplane to separate the data into two classes in such a way that you should have maximum margin as possible, right? You should have a margin, that is distance between support vector and hyperplane. It should be as maximum as possible. It should be as maximum as possible, right? So that is your idea. Now let's see this. Let us see this. So among these different hyperplanes, which is the best hyperplane that you have? Now everybody will understand this and you guys can clearly answer this. Is it H1, H2 or H3? Which one is the best hyperplane that you think? Yes, guys, H3, right? Obvious. Because what is the reason behind that? Why we can call H3 as the best hyperplane? Why is it? Yes, guys. Why we call this as the best hyperplane? Yes, guys. Yes, guys. Because the margin has to be as high as possible. Perfect. Margin would be higher in H3. H1 does not separate data points properly, right? So if I take H1, that is a bad idea, right? If I take H2, it can be a good idea, but the distance between the support vector and the hyperplane is very less, right? But on the other hand, if I just take H3, the distance between my support, my hyperplane and support vector is as maximum as possible, and that can be a great idea, right? So that is what we have for this. Now let's move towards some more detailed case. So for maximum margin classifier, that is support vector hyperplane margin, the data vector point closest to the hyperplane are known as support vector. We already have seen this. Data points because only these 2 points are contributing to the result of the algorithm, right? Other points are not contributing. Because of these 2 points only, I'm clearly able to see that the distance is as maximum as possible, and we can clearly see that if we are able to classify the two groups or not, right? Because of these two data points only. So that's why they call it as support vector, sorry, because this 2 point only results in contributing to the uh, result of the output of the algorithm, and other data points are not. If a data point is not support vector, removing it has no effect on the model, and deleting the support vector will change the position of the hyperplane as well, right? So suppose, just imagine, I am removing this data point, this one, suppose. This is not with me, right? This is not with me. Now, or let's say these are two data points, right? This one is not with me, and this one is not with me. Now, is this the best idea? This is the best hyperplane? Obviously not, because of, I mean, it can be changed, right? The result can be changed. If I don't have this data point, so my hyperplane will change, right? My results will change. So removing this, if the data point is not support vector, removing it has no effect on the model. First point. For an example, if I just I what I've told is, if I remove the support vector, our result will change. But let's say this is your support vector, right? Now, if I remove this data point and if I remove this data point, will my result change? Or if I remove this data point, if I remove this data point, does it impact that does it have an impact with the result out there on result? No, right? Can it be affected if I remove this, then remove this? Will my support vector and hyperplane location will be affected and my result will be affected? No. Are you guys getting this point? Second point, removing the data point which is not a support vector, it has no effect on the model, right? And deleting the support vector will then change the position of a hyperplane. Let's say in this case, this is your hyperplane. You are removing this, right? You are removing this. Then your hyperplane can be like this, right? So removing the support vector machine, deleting the support vectors will then change the position of the hyperplane. That is simple. So till now we have seen margin, hyperplane, support vectors, and what can be good margin. So here they have explained this point that a good margin is a one in which we have all the support vectors have the same distance with the maximum margin classifier or maximum margin hyperplane. But on the other hand, bad margin is the one. It is very close to either class -1 support vectors or class 1 support vectors, very close to either class -1 or class 1 support vector. So that is bad margin, right? Here you can see suppose class 1 is your green data points. And if I just draw this hyperplane, if I just draw this hyperplane, the distance between support vector and this hyperplane is very less. And distance between this class and this is high. So it should not be like this, right? It should be same distance with both the classes. And it should be as maximum as possible, right? Now you have a concept of soft margin, which is also very important one. As the name suggests, soft margin means uh, in real world data, it is not fully linearly separable, right? We'll allow some margin violation to occur, which is called as soft margin classification. And it is better to have a large margin, even though some constants are violated. Margin violation means choosing a hyperplane which can allow some data points to stay on either side, the incorrect side of the hyperplane. For an example, this is your soft margin. This is your soft margin. Sorry, this is your hard margin. So in soft margin, as you can see, we can have data points. We can have blue data point, which is misclassified, which is in the red region. And we can have red data points, which is misclassified and which is placed at the blue region, class 1 region, right? Now, now, uh, it means that it can allow some data points to stay on either the incorrect side of the hyperplane and between the margin and correct side of the hyperplane. Yes or no? And hard margin is the one which does not allow the misclassification or misrepresentation of the data points, right? So that is what we have. Now you have hard margin. You have hard margin. If the training data is linearly separable, we can select two parallel hyperplanes that separates the two classes of data, so that the distance between them is as large as possible. That is your hard margin. If the training data is linearly separable, we can select two parallel hyperplanes that separates the two classes of the data so that the distance between them as large as possible. And in order to have maximum margin, we do this mathematics that is not your that is out of your scope of this particular syllabus. That is out of the scope of our syllabus. We should not discuss that mathematical part. But hard margin is the one which does not allow the misclassification. It is very strict, right? So there are two concepts: soft margin and hard margin. Now, what are the limitations of support vector classifier? So it's a sudden twist in the movie now. That's the reason we have support vector machine, and support vector classifier has some limitation. So what happens is, suppose your data is placed in such a way that by just mere drawing a line or hyperplane anywhere, you place anywhere, it does not allow you the guarantee that you are able to separate two data points. Yes or no? If I draw this, still I have these two data points which are misclassified. If I draw anywhere, if I just draw anywhere, I can see that I'm not able to clearly separate the data, right? These two are misclassified. If I draw here, these two are misclassified. So what should we do this? What should we do for this? Then there comes the idea of support vector machine. So again, very beautiful question that you can expect in the interview. What is the difference between SVM and SVC? So if you have to answer this in one line only one line, support vector classifier, support vector classifier, if the hyperplane classifies the datasets linearly, then the algorithm we call it as support vector classifier. And if the algorithm that separates the data sets by non-linear approach, then we call it as support vector machine. So if my hyperplane, if my decision boundary is non-linear, like this non-linear hyperplane, non-linear, then that is called as support vector machine. So SVM hyperplane is non-linear. SVM hyperplane is non-linear. What about SVC? SVC hyperplane is linear one. SVC hyperplane is linear. Simple. Yes or no? So what is the difference between linear separation and non-linear separation here? Linear separation is SVC, where make use of linear hyperplane, and in SVM we make use of non-linear hyperplane. Now, uh, as of just 2D, if you just observe it in two dimension, it is very difficult to visualize this, right? Even though some of you guys must have got an idea about this, but when I was studying this at the first time itself, it was very difficult for me to visualize this, how we can have a non-linear separation, right? Even though if it is allowed, then why we are not doing over here? So it's not the case. What we do is, this is multi-dimension. This is two dimension, but this is three dimension or four dimension. So idea here is to use a kernel trick, another very important interview question, very important interview question, kernel trick. So in order to understand this, you should explain this in one, two, or 3 points. First point is we should use SVM because SVC has some limitation. So we are using this kernel trick. What is that? It is mostly useful in non-linear separation problems. This shows as follows. What we use is very simple and very interesting one. See now. The idea here, suppose this is one-dimensional space. So points on one-dimensional plane are this. It is represented by a function of x equals to x. They cannot be separated or classified. Now what we are doing is, we are trying to just classify this. If I draw this decision boundary, I'm not able to clearly classify two data because here red points, here green, here red, right? Again, if I just draw this, it is not able to do separately. So what we do is we convert into higher dimensional plane. So if the problem statement is not able to solve by using a normal uh, plane, hyperplane, what we do is we convert that into two dimension. So we convert this into two dimension now. It's a plane. We just bend it, kind of bend this, and we draw a plane over here. This is a plane. Just remember. Again, it is very difficult to visualize. We are going to watch a video for that. So don't worry as of now if you're not understanding. But what we do here is we transform this into higher dimension. We transform this into higher dimension. And we represented this. Now you only know the straight line equation is equals to y is equals to mx plus, right? If your hyperplane is like this, a multi-dimensional curve, its equation, its degree changes, right? Its degree changes to 2. It becomes y is equals to mx square plus b, like that. So it is two dimension, that is your 2D. If it is three dimension, it changes to y is equals to mx cube. So idea here is to, if suppose if two dimension is not uh, able to solve a problem classification correctly, we convert that into three dimension, and there might be a scope, there will be a scope to just classify these two data points by just converting into higher dimension plane. So what we do is we use a kernel trick which will convert your all the problem statements into higher dimensional plane, and that will solve your problem. They take care of, they can now be easily separated or classified. So if I just pass a plane over here, I'll be easily able to separate the red data points and green data points, right? So it's very difficult to visualize. What we'll do is, this is also very difficult to visualize. We will watch one video for that. So I'll quickly share my screen. uh, we'll just try to understand how we transform into two-dimensional, from two-dimensional to three-dimensional, right? So I'll just share one video. You guys can easily get an idea about that. Okay. Hmm. Okay. So what is kernel trick? The best way is to understand this is just to just understand the visualization over here. See, now as I have discussed, I'll just give you a quick preview of what we are going to understand now. Now see, this is what we have in the video. We have a data. We have a data which looks like this. What we do is we convert that into three dimension. Right? This is three-dimensional space. And we pass a plane to that. And then this is our plane which will able to separate the data points. Now see, first they will in the video they will help you out with the two dimension, how it looks inseparable, and how we convert that into three dimension. The conversion into higher dimension is known as kernel trick, and how it is working, we'll see that now. So it's a two dimension, right? Where you can see you cannot separate the blue data points and red data points. You're converting that into three dimension now. So it was a plane, right? This was a plane. Originally it was a plane in which we have a data. And it is not, we are not able to separate this into two classes. So what we do is we convert that into three dimension like this. This is a three dimensional, this one. This is 3D space. Now see what happens. Now can you see if I just pass a plane, hyperplane, this comes your hyperplane, right? This comes your hyperplane. And you can clearly separate after passing a hyperplane. Can you see this? This is your, suppose if I pass a hyperplane like this, and above to this hyperplane we have green red data points, and below to this hyperplane we have blue data points, right? And you're easily able to separate this out, two data points. Your task is done, right? So how do we portray this now in two dimensions? See, if I just place this in my plane now, it looks like this round. Yes or no? But that round is not a what you can say. It's not a decision boundary. It's a two dimension. It's a plane. It's a hyperplane. Yes or no? Now same problem over here. Now just can you just check this and let me know if you are clearly able to visualize this or not? This one, this one. Can you visualize it now properly? Yes, guys. Are you understanding this point? This one? What about other guys? I can see only one response. What about other guys? Our whole idea is to classify these two classes, right? By passing a hyperplane. So in two-dimensional space, it is not possible. We convert this into three-dimensional space and pass a plane. That is your hyperplane. And this hyperplane will clearly separate this green and red data points. But in order to show that in two-dimensional space, it looks like this, where this is your hyperplane. It is like this, and this is your hyperplane, right? Below to this. So this becomes round. So that's why it is they have shown this as a part of round over there, right? So in a more precise manner, nonlinear can be explained by another visual representation as below, where it can be clearly seen that how the data point which is not able to linearly classified converted into higher dimensional. This conversion of conversion into higher dimension is known as kernel trick, right? and then get separated linearly in higher space, which is back non-linearly separated in the original dimension of lower space. If still you are confused, I have shown you the video for that. You still need more clarity, see the below video which I have shown for crystal clear idea how the data are transformed into higher dimensional, and from there how linearly got separated, then back to the normal plane, right? So that is your kernel tree. So there are famous kernel and most frequently used for nonlinear kernels in SVM are polynomial, Gaussian, and sigmoid. It's again a mathematical part. You don't need to care about that. The figure that we have seen, the video that we have seen, it's a figure of polynomial kernel, right? And as you can see, user they have written down the comment as 43 seconds are quickest way to understand what's going on in SVM, right? So this one is your polynomial kernel, and you don't need to worry about this. You should only know there are three types of kernel: polynomial, Gaussian, radial basis RBF, or sigmoid. So radial basis function RBF, sigmoid, and polynomial kernel, which we use to solve the problem of non-linearity. And this is in a quick sense of what SVM is, which we already have discussed. It's again a self-explanatory diagram, right? And these are the advantages, these are the disadvantages. Advantages are it is more effective for higher dimensional space. It works well even with even unstructured and semi-structured data like text, images, and trees. It handles the nonlinearity data efficiently by using kernel trick. Nonlinear data it usually handles perfectly. SVM has an L2 regularization feature, so it has good generalization capabilities. Don't worry about this L2 generalization. I'll just mark it over here because we have not seen that. Again, it's very important part. Regularization, which is something which we are going to see in the next session. There are a few ways to uh, maximize the, in order to maximize the accuracy, we have few different ways. So one is this, second is hyperparameter tuning. That is what we have. And third is cross validation, which is again a separate topic. I just want to take it separately so that we should feel this as the important one, right? So that's the reason we are not indulging this into the machine learning model itself, right? Uh, so it has good generalization. Don't worry about this. We'll see this. SVM, a small change to the data does not greatly affect the hyperplane. Hence, the SVM and the SVM model is stable, right? And these are the applications. These are the disadvantages of SVM. It is not suitable for large data set. It is sensitive to outliers. It is the hyperparameters like cost and gamma is not easy to fine tune and also hard to visualize their impact. SVM take a long training time on large data set. SVM model is difficult to understand and interpret by human beings, unlike decision trees. And one must do feature scaling of variables before applying SVM, right? Now, what are the applications? We have handwriting recognition, we have face detection, we have text and hypertext categorization, we have image classification, and we have bioinformatics, which is protein classification and cancer classification. So it is widely used for complex problem statement, right? Your normal machine learning models, linear regression, logistic regression, will fail substantially in this face detection and handwritten recognition or text and hypertext categorization because it's a complex problem. Even though we go with advanced methods like deep learning and much more to solve these complex problems, but idea here is to just understand SVM will also be useful for us to cater this complex problems, seemingly complex problems, right? So that is what the idea is. Now, yeah, this is your data set. which we are going to see, just a practical implementation of SVM. Now, what you can do is we'll take a quick break of 10 minutes. I already have given this on your drive, right? You need to go this, you need to use this one more time, right? I mean, go through this one more time, revise this one more time. We'll have a break, short break of uh, 10 minutes. At 10:05 exactly, we are going to start with the practical implementation of this SVM model, right? So let us have a break now. I think I was on mute. Okay. What I was discussing is I have just uploaded this data over here. It's gonna be very important project for you where we are going to see how to unzip the file, and it's also very useful project. So let's not waste our time on discussing further points. Let us directly start working on importing necessary libraries. So I'll just put heading as importing the necessary libraries. I'll just upload the data over here. The data is, I'm just directly uploading the zip file because we are understanding here, we are going to understand how to unzip the file, right? So we are going to import pandas as PD first, import numpy as np, import matplotlib as pl. I think that will not require, will not use that. We are going to use image extraction libraries. We are going to import OS from zip file. We are going to import zip file, and we are going to use image reading libraries from PIL. We are going to import image. I'm going to import matplotlib dot pyplot as plt. Yes. And I'm going to import the images now. It's time to import these images. So let's put heading as importing the images. I'll just pass file underscore name, which is exactly equals to this. Yeah, so we have to give a path. It should be like this only. Expression underscore images underscore dataset. That is my image file, right? And the extension is zip file. The destination path for me, for us, is again the expression images, because in this expression image dataset, we have expression images that we are going to see. If you just unzip this file, you will be able to understand we have expression underscore images folder in that. Now, I'm going to open the zip file in read mode with zip file. I'm going to pass a file underscore name in that. That is R as zip. And I'm going to extract all the files from zip file. So I'm going to print this extracting underscore images dot. So once it is done extraction part, it will be notified to you. Now I'm going to check if the destination path exists or not. So if not os.path.exist destination underscore path, this I'm going to zip.extract all path is equals to destination underscore path, and I'm going to print done. I'm going to print done. And if it is not done, will write down our destination path already exists, right? So if I just press this, run this, it will unzip this by using this with zip file this. And can you see this? It is unzipped. We have expression images now over here. In that, we have different images file, right? And in this images file, we have several images. It is, I think, more than 200 images as part of your data, right? As part of our data. We have, I think, more than 200 images. So that's what it is. The file that I've given, this zip file, you can download this, unzip this in your file itself, in your file explorer, and you try to see the images, each image out there, right? We have uh okay, I'll just show you this data sets as well, so that you will be able to understand. It's very interesting project. Training materials, SVM. Yeah, this one, this images I'm talking about. See, can you see we have at least, I'm not sure the quantity or here. Okay, just a minute. Let us see properties. 213 file, right? We have more than 200 file, I told you. And each file, each photo has some expression with it. So this is, let's say this is this particular image is happy, right? This one is sad, let's say, right? So by just having a look at the image itself, we are our model is to we want to build a model which will identify the expression image. So this data set is of, I think, a Chinese university, where the student, these are their students, they have just clicked their photos of having different expressions, and they just try to understand the SVM model. For that reason, they have just created this data set, small data set. So this is amaze, right? This is shocked or amaze. This expression is shocking or amazing or amazed. This is boring or something like that, right? So end to end, we have more than 200 images in that. And now, just now, let's start working on this. Okay. So I just want to read one image, just one image. I'll put heading as reading the image, and IM is equals to image, the library that we have imported to load the image. And the image that we are going to use is anything is fine, but it's in this expression images, in that we have images folder. In that, I want to use this k.n1, k.n1 first file, that is dot 39. So I'll just write down that path, dot 39 TIFF. TIFF is the extension that you have for that images. And now it's time to just read the image, which you can see over here, right? So that is what your image is. Now, uh, parallelly, we have the expressions image, right? What does it means is, in this expression images, we have data.csv. Can you see this data.csv? So we want to read this file. So pd.read underscore csv. The file is this dot expressions underscore images underscore data dot csv, right? And I need to check df.head as well. Need to write on df.head so that you'll understand what this file is all about. This file is having a very beautiful explanation where this particular image is angry. You can see this is angry, right? This particular student, she is angry over here. So this is angry expression. Likewise, we have angry, disgust, and if you just see facial expression value counts, what are the different expressions that we have uh, in facial expression column? How to check that? We have value count function, yes or no? So we'll use that value underscore counts, open and close bracket. You'll be able to see we have fear, happiness, sadness, angry, neutral, surprise, and disgust. These are the facial expression criteria. And we'll quickly check the info of the data where we have file path column, we have student column, we have facial expression column. And now it's time to go for data preparation. data preparation for model. Whole idea of machine learning is to convert everything into numbers. So whether it should be image, whether it should be text, whether it should be anything, we have to convert that into numbers. That is our first primary steps, because our computer will not understand the image, right? It will read image as a number. So let's convert that image, these images into number. We'll pass a loop for I in range. How many images are there? 2, 1, 3. Uh, we'll write on path is equals to, in quotes, expression underscore images plus df dot iloc of I of 10, sorry, 0. First image, im is equals to image dot open path, and I'm going to convert the image into numpy array of shape 256 by 256 images into a one-dimensional array of length 65536. And I'm going to write down, it should be here itself. It should be here itself. Im underscore array is equals to, we're converting the image into array of 256 by 256. So np.array is what we are going to use. np.array. In that we'll pass im, we'll pass reshape function to convert this into 256. If we just multiply 256 into 256, the output is, the size is, just try to check this. 256 into 256. What's your output? It is 65536, right? So we should write down reshape 65 to 256 into 256, that is 65536. And I'm going to append what im underscore array in X. That is a blank list. Oh, this should be here. Yeah, right. So that is our path, and one by one for all the images out there, we are converting all the image into array. This is little complicated, but don't need to worry about this. You should understand only the logic. So first of all, we are creating an empty list. In that, we are passing this for loop. What it will do is, it will read everything in this IM. So all the images, 213 images, will be a part of IM, and that we are converting into an array. So this is your array, right? Now, after converting into array, if you just find length of this array, that is len of x, that is your 213, right? And then if you find length of x of 0, that is 65536. And then I'm going to standardize the data, or feature scaling. I'll do feature scaling. I'll write down scalar is equals to standard scalar. Yes. Open and close bracket. X is equals to scalar dot fit underscore transform. In that we are going to pass x. And if you check what is there in x, standard scalar is not defined. Okay. I think the package is, we should import that package. Right. Right. So let us import all the necessary packages over here only. Data pre-processing libraries from scalar dot pre-processing. I'm going to import standard scalar, comma, label encoder from a scalar dot model underscore selection. I'm going to import train underscore test underscore split, comma stratified k fold, comma grid search. See. Then I have ML model from a scalar dot svn. I'm going to import svc. Then I have model evaluation libraries from sklearn dot metrics. I'm going to import accuracy score, comma confusion metrics, comma classification report. I'm going to import warnings dot filter warnings in quotes ignore trend test split. So these are the necessary libraries. That standard scalar spelling is wrong. Yeah, should be scalar. Yes, these are the necessary libraries that we are uh, going to use. Now it's time to do the scaling. Because if you see in this array, everything should be in single range, right? That's why we use scaling. So that's why we have done scaling. And now if you check after scaling, if you check what is there in X, so it is scaled in a single range. Everything is in a single range out there from 0 to 1 or in a single unified range, right? Now it's time to uh, do the encoding because in your data, that is your df.head, we have some categorical columns, right? We don't have any numerical column out there. Do we have any numerical column? Student is also not numerical. Facial expression is also not numerical. So we have to convert that into numerical first before fitting the model out there. So what we'll do is we'll put heading as train, comma, test, comma, split, and we'll pass x underscore train, comma, x underscore test, comma, y underscore train, comma, y underscore test is equals to train underscore test underscore split x comma y comma test size is equals to 0.2 comma random state is equals to 42 or any random state. Y is not defined, right? Yeah, we have not done the encoding, right? That is remaining. So let's do encoding first. Encoding the target variable. How do you do encoding? We'll call a package. Here we are going with the label encoder. Open and close bracket. Y is equals to le dot fit underscore transform on facial expression. And then we will be using trend test split, this one. And then we'll write a model is equals to SVC. Yeah. Here, if you go to official documentation of SVC or support vector machine, anything is fine. Support vector. All you need to do is, suppose you don't know which parameter or you don't know what we need to pass inside this SVM. So how do you take help from the official documentation? We'll see that. So we'll write on SVC, sklearn official documentation. And you can see here, we are getting this. So if you go to the official documentation out there, you'll find that here we have C, we have kernel, we have degree, we have gamma. So you can pass anything. I'll just pass kernel is equals to only use, I'll be using one parameter, that is, I'll go with linear kernel. You can go with any parameter out there, polynomial, RBF or sigmoid. Anything is fine. I'll go with the linear one. You try and experiment with other kernel out there. That can be your homework for this particular project. And I'll just fit the model on X-train and Y-train. And then I'm going to do the model evaluation. So y underscore pred is equals to model dot predict. We predict on X test, right? And then I'm going to find accuracy score of y test and y pred. And then I'll try stratified k fold CV. I'll use prediction for new data. I'll add on plt dot mat show x underscore test of 15 dot reshape 256 comma 256. So what we'll do is of that particular X test data, we are just taking 15th image, any random 15th image. We don't know which image is a part of 15th image. We are just taking a 15th image. That is this. We are reshaping that into 256 by 256. This is a little bit hazy because we have done standardization, right? So we are just compromising the quality of the data by using scaling. Scaling uh, also gives you scaling. What it does is it suppose just take a hypothetical example. Suppose you have a large image, right? Very large image, and you have small images. The images are not uniform. So you kind of scale the data, like one image is large, another image is small, third image is having different dimension, fourth image is having different dimension. So you modify the data, right? You scale data into only one dimension, that is 256 by 256. Suppose. So all the images in your array will be having same dimension, that is 256 by 256, right? As a result of this, uniformity is maintained, accuracy is good. But let's say, let's say you have a large image, and that large image you are converting into 256 by 256. So will not there be any chance that quality of this data will be reduced? You are compromising the quality, yes or no? Because large image, we are just cropping that into small image, or we are just scaling that into small image. So don't you think quality of the image is compromised over here? Don't you think, guys, quality of the image is compromised? Yes or no, everyone? Right? So that's what we have. That's what we have. Now the main task is we are using this model dot our model to predict the X test of 15, and we'll just do inverse underscore transform of this model dot predict, because this is an array, right? We want to convert this into an expression, right? So inverse transform will do converting an array into this one, X underscore test of 15. So if I run this, what I'm getting is surprise. So isn't it this expression is surprise, yes or no? So likewise, we will do it for multiple images. We can do it for multiple images. So you can take this plt.mat show. Instead of x underscore test 15, instead of x underscore test 15, we'll just take x underscore test 5. Run this. Fifth image. Now, what is the expression of this image? What is the expression of this image? We don't know, right? So what we'll do is we'll just make use of this model.predict x test. It's in which array? It's in array number, sorry, not 15, it should be 5, right? Here this time it should be 5. Fifth image is in array number 0, right? And you'll transform this into a facial expression. So it's a surprise again. So likewise, you can change. Now let us take 26, suppose. This is, I think, fear. The expression is fear. So if I just write down 26, this is fear, right? Again, take and change any figure, any dimension. 34, 34 is disgusting. Disgust. I am interested to just check, do we have any happy or not? Let's check. Oh, it is only out of out of bounds for axis 0 to. Okay. Maximum we have 43. 43 means it should be 42 only. This is again fear. Let's do it for try 30. Okay. Let's try 30. Okay. So here, if you just write down 30, 30, as we also know, but we need to create a model. So it is happiness, right? Are you guys getting this now, everyone? What we are talking about? Yes, guys. Do you have any questions in this? Anyone?
In that 37th line, so model that predicts, so giving that array number is 26. So how it is taking?
I directly have taken 30. Now,
Oh,
what we are doing is
okay.
model.predict.x underscore 30. I am directly taking over here, no?
Okay.
So anyway,
Mhm.
this step is not necessary. That's what I was. This is not necessary, no? See, this thing, model.predict x underscore test 30, we are passing it in transform. No, we can directly pass this. There's no need to check array 3. It's just for our understanding. This is just for our understanding. Like we are just going stepwise. Without calculating this, we can directly feed to our model. No, our model will calculate that this is an array number 3, and array number 3, it will directly transform this. So this is not necessary, but this is just for our understanding. We are doing that, right?
Yeah.
So actually, Vipul, we are actually training the based on the images, the 50 images. We are training and getting the result back.
See, what we have done is, first of all, uh, we have these images and it's linked with the expression, right? We have this data given with us for us. Like this image is angry, this image is angry, this image is disgust. But we want to convert our image into numbers first. Then after converting in numbers, we want to convert this into array. so that it will establish a link between this image. This image is as an array, right? This is in number, right? So
Yes.
it will establish this connection between this and that particular image as form of a number, and then it will try to predict that it is angry. This is yeah, like that.
Okay. Okay. So if we give any other images among the 50, it will give the answer also, right?
Uh,
Or
what you
only we can give for now, only we can give the among the 50, we can give any one of the images.
Yes, but that will be having different steps, because you need to convert you need to have a sample data for that particular image. In future, let's say you have taken an image and you have to pass that in your this data first here, then only you'll be able to predict. So
Oh,
directly new image, you cannot directly ask to predict the facial expression of that. You have to
so
have this.
before it's detecting, we need to upload our sample images and then we can try to predict. That's what you
Right.
are saying. Yeah. Okay. Fine. Thank you.
But anyway, as this is a capable model, anyway, it can predict the future data as well. Like the data in which we don't have facial expression, it will try to predict that.
Okay. 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 Fine. No problem.
That is something which we are going to use, see in our CNN part, right? Deep learning part. Again, that is very interesting. So if you just see your syllabus, you will be able to see it is and at the end, last part, deep learning and that. So there we are going to see very powerful model, CNN model, which is a part of deep learning, uh, which we use to predict the images. So that is something which we use nowadays. We will not be using SVM model to classify the images because we have some powerful models, no? This has become obsolete. Is it clear now?
Clear. No problem.
Excuse me. All right, let me just have a look at our syllabus now. What is remaining? We'll just see. I'll just share my screen. Does it mean that accuracy would? Yes, accuracy can change. Yes, if we use different kernels, obviously accuracy will change. But that does not mean that we should use that kernel only. Any kernel is fine for us. But it has some applications that is very detail part, and it is not necessary for you. We use RBF kernel for some application. We use sigmoid kernel for some application. We use linear kernel for some application. But its accuracy would improve if we use kernels like sigmoid kernel over linear kernel, where the fitting of data point will be flexible over the hyperplane. There might be chance that you will be able to increase the accuracy. So when should we use which kernel in SVM? Over here, it's very detailed, it's not necessary. So generally linear kernel should be used if the data is linearly separable or has many features. Polynomial kernel if it has non-linear patterns or interaction between features. RBF kernel if it has complex and non-linear patterns or clusters. And a sigmoid kernel if it is binary or looks like logistic function. So that's why I told you, as this is very simple problem, any kernel is fine. But just try exploring different kernels as well and just check the accuracy if it is increasing or not. For us, it is 83.72, which is significantly fine, but not very good. You can try a different kernel and try to uh, increase the accuracy or check the accuracy if it affects or not, right? That is one thing. So you can try exploring this, even though it is beyond your scope as of now, because we are just dealing with the simple models. So it has some mathematical part and it is also not required. That's why we have not taken this. But application side, you can just have a look at this. But as I have told you that we have not discussed this random search CV, grid search CV, cross validation. At that time, you'll get an idea ki how we increase the accuracy. Not only we use kernel, we use different models, different techniques to increase the accuracy. And that is what the valid and legitimate methods are, not only just changing the kernel and parameters, right? So this is something, hyperparameter tuning and cross-validation and grid search CV, which is very, very important part. That's why I want to take this separately in our session, where one separate session will be just separately allocated to these techniques to increase the accuracy. At that time, we'll discuss it in more detailed way, right? And as of now, you just read this. Linear kernel are suitable for high dimensional data, linearly separable data. And but this is not just a not a hard and fast rule to just go with linear kernel at this time, RBF kernel at this time itself, because nobody will be able to remember this, right? So the best way, simple and naive way, is to go with the any kernel out there and build the model. Because anyway, we have different techniques to increase the accuracy. Yes or no? So this is not that much effective. Select any kernel, you'll only hardly find increase or decrease 1 to 2% of the accuracy. Sometimes if we have simple data, chances might be that you will be able to increase accuracy significantly. But this is not real world data, right? Real world data will be having a lot of parameters, lot of values. Not only 200 image, we'll be having 10,000, 1,000,000 images like that. So that's why I'm not giving much more focus on these kernels. Yes, now what we were discussing is, see over here we have convolutional this thing, convolution activation function, max pooling, this computer vision with convolution neural network. Here we are specifically going to deal with what? Deal with a very advanced model of identifying the images, right? At that time we are going to see that. Okay. Do you guys have any other questions? Let me check the modules. So module 9, I think still remaining because they have given everything in module 9, which is very difficult to complete in 1 or 2 sessions. So model building, assessment, improvement, diagnosis, multiple linear regression is done. Random forest and decision trees are remaining, just small part of this. Session 16 is completed, but still K-means clustering is remaining, KNN is remaining. See, what are these? These are different models, right? So for one machine learning model, at least we have one session separate. If it is a basic one, like your knife bias and SVM, that was the simple models. That's why it took one session. But linear regression is a very vast topic. So it will require 2 sessions. Logistic regression require 2 sessions. So it's very difficult to complete all this in very one session, even though they have allowed us to go beyond this specific timeline. So that is good point for us. But KNN, K-means is remaining, these 2 points. Random forest, descent trees, these two are remaining. Then dimensionality reduction, obviously this is a separate topic which will require 2 separate sessions at least, that we're going to see. And then we are going to start with the neural network. So today is being only day number 24 and we are going with the 17th session. Okay, that's fine. All right, do you guys have any questions now? Anyone here? Anybody have any questions? Anybody wants to discuss anything? You can discuss. Yes, if you want to discuss anything, you can discuss, because I would like to know if you have some input for me that we should follow in our session. That is also something uh, which I will admire or appreciate. Yes. Can you again explain how we train a model? Which model, Kanan? Which model?
Well, so the steps to train that one. Can you again explain the steps to create a model and train it?
Just a minute.
Ah,
Okay. What is your question? Can you please come again?
So can you explain that how to create a simple model and train that model? So you have some steps, right? So in the last class we have discussed.
Which one? This one. Which one you are talking about? Last class.
It's basically how to like create a model and train that model. So you're giving that x underscore train, right? So that
Mm-hmm. Yeah, yeah. It's common, no? It's common for all the models out there. Now today is our one, two, three, four, fifth model building. Today's fifth model. So still it's not clear for you. Like
yeah.
linear regression, we have seen multiple linear regression, logistic regression, we have seen naive bias. Still it's not clear. Okay, no worries. I'll just explain this one more time. See, first and very first thing is what we do is we import the necessary library, right? So in that we have NumPy, we have pandas, we have matplotlib, we have cball, and we have multiple libraries that we have to deal with. Then we read the data, yes or no? So we write on df is equals to pd.read underscore csv and the data file. We read this file. We check the head of the data, which weekly check if it has outliers or not, if we have null values or not by df.info, df.describe, right? We plot the box plot to check if we have outliers or not. We remove the box plot. Sorry, we remove the outliers. We remove null values. We treat the missing values. Yes or no? Once this is done, like your model, your data is all set to fit the model. Even though if scaling is required, we'll do that. If sanity checks are there, if the specific column has specific data type or not, if it is not there, so we need to change the data type. Encoding is there, so n number of things are there which are part of data pre-processing, which we deal with the which we'll deal with whenever we are interested to clean the data, right? And now if everything is set, then we go with the model building part. But before that, we do the trend test split. So the idea here is to divide your data into two parts, not equal two parts, because training should be as higher as possible, because that is something on which your model ideally will train and study all the patterns in the data, right? And then we just use this test data. We just use this test data to check and predict if particular data is correct, it is correctly predicting or not, correctly predicting it or not. So that's why here also we have converted into text test, right? If you just see, we are doing trend test split. Why? Because same thing, we don't show test set to your model. First point, we'll not show this to a model. We'll train our model on train set, and we'll ask our model to predict the test set, right? So that's why this particular image is a part of test data, which is completely unseen to your model, but you're asking what will be the you're asking to predict what is the uh, expression for this particular image. So as it is not completely seen to your model, it doesn't know, like we are not showing this image to our model. Just understand this in simple term. Your model has not seen this data. We are just asking to predict what will be the prediction of this. We are making use of model to predict this, and it's correctly predicting surprise. So in future, let's say if we if we get a data which is completely new to our model, it will predict it properly, right? So even though this is a part of our data, but that is a part of our test set, which is not seen to our model, which is completely hidden to our model, which we only use to check and predict, to check the performance of the model. This test set is completely used to check the performance of our model. So we'll take this image, let's say image is 50, which is a part of test set, and we'll ask our model to predict what is the expression of this, and it will predict it properly with what percentage of accuracy? With 83.7 percentage of accuracy. Right? So that's why we do trend test split. That's why you used x underscore train, x underscore test, y underscore train, y underscore test. And in x, you have all the independent variables which we use to predict the target variable. So for an example, if you are interested to predict the expression, right? So in our data here, in our data, the facial expression will be your target column. That is your y. So in y, what will be there? Facial expression will be there. In your x, what will be there? You will be having different columns, like you'll be having file path, student, which is a supplementary columns to predict the target variable. So these are known as independent columns. Yes or no? Right? So that's what it is. Simple. The having done this, model build, we'll go with the model building part, where we'll call a package by official documentation of uh, sklearn. Suppose if you are going with a linear regression, you'll go and write down linear regression sklearn official documentation, and these are the, here you'll find a package. Simple. And that package you'll copy and you'll create an object. So model is equals to linear regression, open and close bracket, right? Second step is model fitting. So which subset we use to train the model? We use X-train and Y-train. Third is model prediction. We use X-test to predict what is there in your model. And third is model evaluation. That is what you are going to check accuracy score between Y-pred and Y-test. Why Y-pred and Y-test? Because by using X-test, which is not seen to a model, will predict something. Suppose this is predicted and this is actual. This is test data. Suppose your model has predicted happy as the facial expression. This is also happy. Suppose this is sad. This is also sad. This is neutral. This is also neutral. And suppose this is disgust. This model has predicted discussed, but this was not discussed. This was neutral. So what will be your accuracy out of 5? Out of 4, 1, 2, 3, 4, your model has predicted 3 correctly, right? So accuracy becomes 75%, 3 out of 4. So likewise, you calculate your accuracy. That's how your accuracy is calculated. Is it clear? So out of 213, your model has 83.7 accuracy. So 0.8372 into 213. 178 out of 213, 178 correct predictions will be there by your model. Right? Is it clear?
Yes.
Okay. All right then. Okay. Do you want to discuss anything more? Yes, very good point, Darshini. That's what I was going to teach. For n-dimensional space, your hyperplane is n minus 1. Very good. So suppose uh, you have two-dimensional space. So your hyperplane is line. If you have three-dimensional space, your hyperplane is plane, a plane. If it is 4D, hyperplane is 3D. That is what kernel trick is, right? I'll just explain you this point in just a minute. So it's a thumb rule that for n-dimensional space, we have hyperplane which is equals to n minus 1. It did not. It's very good point that, I mean, very good and important point. In SVM, if the plane is two-dimensional, and by using two-dimensional space, uh, if the data point is clearly separated out by using by using a line, so the line is one-dimensional, right? But the space was two-dimensional. Now here in this diagram, here in this diagram, uh, just a minute. Why it is not happening? Yeah, here in this diagram, if you see, now this is a space, three-dimensional space. Yes or no? This is three-dimensional space. But your hyperplane is two-dimensional. That is a plane. So it is always n minus 1. It will be always n minus 1. And beyond this, you're not able to clearly visualize by your eyes. We cannot see 4-dimension, 5-dimensional data. So that's why we not go beyond that. But your computer can go and deal with that dimensions as well, right? So that is a thumb rule that for n-dimensional space, your hyperplane is n minus 1, right? All right then. Anything more you want to discuss? Yes, guys, we still have 5 to 10 minutes. You can ask questions and we can discuss with that. Yes, guys. Do you guys have any questions, any doubts? All right, then we'll stop here for the day. Thank you, everyone. Happy learning. Try this out, this particular project that we have done, no? You have to try this, practice this multiple times so that you can become comfortable with this and you can able to explain this in the interview itself, right? It's going to be very, very crucial one. Sure. ठीक है. All right then. Thank you. Happy learning. Bye.
Okay,